Physics-informed neural networks explain. Physics-informed neural networks, or PINNs, blend traditional neural network learning with the laws of physics. This video provides an overview of how neural networks work, how PINNs integrate physical laws into their learning process, and why this makes them especially powerful for certain real-world applications. We highlight key advantages of PINNs, such as better generalization, data efficiency, and physical consistency, and give examples of where they shine. Neural networks are a form of artificial intelligence inspired by the human brain. They consist of layers of interconnected neurons as simple processing units that adjust the strength of their connections based on examples they see. In essence, a neural network learns a mapping from inputs to outputs by training on data. For instance, given many examples of house sizes and prices, a neural network can learn to predict house prices for new sizes. The more data it has, the better it can capture complex patterns. However, traditional neural networks rely solely on data. They have no built-in knowledge of the real world or physical rules. This leads to a few shortcomings. They typically need large amounts of data to learn accurately. With only a small data set, a conventional neural network might either fail to learn the pattern or learn it incorrectly. The second shortcoming is poor extrapolation. If asked to predict beyond the range of data they've seen, they often give unreliable answers. For example, a neural network trained on temperatures from 0 to 30 degrees C might give nonsensical results if asked about 100 degrees C, because it has no concept of physics, like what happens to water at boiling point. Third issue is that there is no guarantee of physical sense. Because they don't know any scientific laws, standard neural nets might produce predictions that violate common sense or fundamental principles. For example, a naive model predicting a ball's motion could output the ball flying upward forever, simply because it was never told about gravity. In summary, traditional neural networks are powerful pattern finders, but they only know what the data tells them. If the data is limited, noisy, or doesn't cover certain scenarios, these networks can falter or suggest implausible outcomes. Physics-informed neural networks take the basic idea of a neural network and add a significant twist. They also learn from known physical laws, not just data. In practice, this means that when a PINN is being trained, it is guided by two teachers, the data and the equations of physics that apply to the problem. A PINN's training process includes the usual step of matching the provided data points, like any neural network would, but it adds an extra requirement. The network's predictions must also obey certain physical equations. These equations could be well-established scientific laws, such as Newton's laws of motion, conservation of energy, or fluid dynamics equations. The training algorithm actively penalizes the network when it produces results that break the known laws. As a result, the PINN learns to satisfy the physics equations at the same time as it fits the data. Think of it this way. A traditional neural network is like a student who learns by memorizing answers to practice problems, while a PINN is like a student who learns the practice problems and also understands the formulas from a textbook. The student with the textbook, the PINN, is more likely to get the right answers even for new, unseen problems, because they grasp the underlying principles. How does PINN work, in simple terms? We start with a neural network model, just as we would normally, by providing it with some data. We also provide it with the relevant physics equations for the problem. The network adjusts its internal parameters to minimize two things simultaneously: the error between its predictions and the data points, and the error in satisfying the physics equations. By doing this, the PINN finds a solution that fits the data and remains true to physical laws. For example, imagine training a model to predict the height of a ball tossed into the air over time. We know from physics that gravity causes a constant acceleration downwards. A traditional neural network might need many data points to learn the exact trajectory and might still guess incorrectly outside the range of the training data. In contrast, a PINN would be given the equation for gravity as well. Even if it sees only a couple of data points of the ball's flight, the PINN will use the gravity equation to fill in the blanks, ensuring that its predicted trajectory is a realistic parabola. In short, the PINN won't forget about gravity. Its predictions will automatically follow that rule, leading to an accurate path for the ball that makes physical sense. PINNs have key advantages over traditional neural networks. A physics-informed neural network generalizes better, works with less data, and produces physically meaningful results. These strengths make PINNs particularly powerful for problems where purely data-driven models struggle, typically in domains that have well-known governing equations but limited data. In conclusion, physics-informed neural networks represent an exciting development in how we model the world. They take the flexible learning ability of neural networks and anchor it with the firm moorings of physics principles. This combination yields models that learn faster and with less data, thanks to built-in knowledge, generalize to new situations more reliably, and respect known truths about how the world works. The key takeaway is simple. Instead of treating a neural network as a black box that might unpredictably veer off, PINNs keep the AI on the rails by teaching it the laws of nature. This makes them especially powerful for tasks in science and engineering, from designing safer cars and predicting the weather, to advancing healthcare and beyond. In fields where trust and accuracy are paramount, PINNs provide a promising path forward, ensuring that our smart models play by the rules of reality while still learning from data. Thank you for your attention, and see you soon in the next video. Please let me know your opinion in the comment section.